Hi, welcome to the Euclidean Geometry 101 course, part 5 in the chapter about triangles. We will end this chapter with two propositions valid for every triangle. Intuitively, we can see that when you go from start to finish in a straight line, your journey will be longer if you first go to another place before going to the finish. Well, that's what the next proposition, number 12, is about. Every side of a triangle is smaller than the sum of the two other sides. A triangle has three sides and the proposition is obvious for the two smaller sides. Let's call BC the largest side in ABC. We need to prove that BC is smaller than the sum of BA and AC. We use a similar method to the one used in previous proposition by constructing an isosceles triangle. We extend BA with AC prime and the extension has the same length as AC. Connect the endpoint of the extension with C. This construction guarantees us that the triangle CAC prime is isosceles. So angle C prime is equal to angle N, the base angles. In triangle BCC prime, we know that angle N is smaller than angle BCC prime because the leg AC lies in between the angle BCC prime. So angle BCC prime is greater than angle C prime. And from proposition 11, we know that opposite a greater angle lies a greater side. So side BC prime is greater than side BC. Now BC prime is composed of BA and AC prime, and AC prime is equal to AC. So BC prime is equal to the sum of BA and AC. Replacing BC prime in the previous inequality, we get that the sum of BA and AC is greater than BC. There is an obvious corollary to this proposition. The proposition said something about the sum of sides in a triangle, so it goes without saying that we can state something analogous about the difference between sides. In that case, we can say that every side of a triangle is greater than the difference between the two other sides. An important remark follows all these results. If you are given three random straight line segments, it is not guaranteed that you can make a triangle with them. Every straight line segment must fulfill the two sum and difference conditions. Namely, if A, B and C are the three sides, then A must be smaller than the sum of B and C, and A must be larger than difference of B and C, etc. Let's illustrate that with an example. We have three straight line segments A, B and C. Is it possible to make a triangle with those three? So we test the set of sum and difference conditions. First, we'll test the sum conditions. A is shorter than B plus C. B is shorter than A plus C. And C is shorter than A plus B. Now we'll test the difference conditions. A is longer than B minus C. B is longer than C minus A, and C is longer than A minus B. The six conditions are fulfilled, so we can construct the triangle. The final proposition in this chapter sounds like: When two triangles have two sides that are equal, and when the included angle in the one triangle is greater than the included angle in the other triangle, then the third side of the first triangle is greater than the third side of the second triangle. Behold the two triangles ABC and A'B''C'. The sides AB and AC are equal to A'B' and A'C' respectively. The included angle A is greater than the included angle A'. We need to prove that side BC is greater than B'C' for the proposition to be true. Using an already familiar technique, we move triangle A'B''C' on ABC in such a way that A'C' coincides with AC, the point A' coincides with the point A, and the point C' coincides with the point C. We execute this in such a way that B' lies in the same side of the straight line AC as B. We rename the point B' after the transformation D. Our setup is now ready. As angle A' is smaller than angle A, so AD, which is the moved segment A'B', lies inside of the angle BAC. Now we construct an angle bisector of angle BAD. The angle bisector intersects BC in the point E. Draw segment ED. We now see that the triangle ABE and ADE are congruent. The congruency case is side angle side. The side AE is a side they both have in common. The side AB equals AD, because we constructed it that way, and the included angles are BAE and EAD, which are equal because they are the angles of the bisector construction. And therefore, side BE is equal to side DE. With this intermediate result, we can now look at the sum of sides in the triangle EDC. In this triangle, we know that the sum of DE and EC must be greater than DC. We can replace DE by BE, and we can replace DC by B'C'. Doing so gets us the inequality stating that the sum of BE and EC is greater than B'C'. The sum of BE and EC is equal to BC, and so we get that BC is greater than B'C'. And that's what needed to be proven. Here too, the converse proposition is true. When two triangles have two equal sides and a third side that is not equal, then there will be opposite the greater side a greater angle. We now start with two triangles ABC and A'B''C', where side AB and AC are equal to A'B' and A'C' respectively, just like in the direct case. But now we start with the given that side BC is greater than side B'C'. We need to prove that the included angle A is greater than the included angle A'. Let's prove that A is not smaller or equal to A'. On the one hand, if angle A were equal to A', then the two triangles would be congruent as a side angle side case, because they would have equal included angles between equal sides. And so in that case, BC would be equal to B'C', and that's not possible. On the other hand, if angle A were smaller than angle A', then BC is smaller than B'C' because of the direct proposition. And that's contradictory to the given. So angle A must be greater than angle A'. Well then, With this, we end the 5-part chapter on triangles. Next time, we will look into the properties of more general polygons. If you like this series, consider subscribing to my channel.